So yesterday we got this introduction to vectors in 2 space and 3 space, so in the XY plane and XYZ space, and how we can do arithmetic with vectors and what that arithmetic represents. So the main ideas from yesterday, some of the examples of the main ideas from yesterday included that we can use addition and subtraction of vectors to do things like determine a parallelogram that those vectors create, or to find a vector that takes us from point A to point B. So when we looked at those arithmetic topics, let me just open it up here one more time, just as a reminder, right, that when I'm subtracting vectors, what I'm really finding is a displacement between 2 points. When I'm adding vectors, I'm calculating what we sometimes call a resultant, and that together, the sum and difference of vectors constitute the 2 diagonals of the parallelogram that those vectors form. So in a way, we can use addition and subtraction to calculate the lengths of these diagonals in this parallelogram. A little bit later on today, we're going to develop a vector technique that's going to let us find the area of this parallelogram, which is a new kind of geometry that we're going to be able to do, as well as a vector technique to find the angle in between the vectors p and q. So today, yesterday was sort of about lengths and distances and displacements. And today is going to be more about angles and areas, so we get a little bit more on that sort of geometry side of things. We also saw last time what scalar multiplication does to a vector. It changes the length of a vector and possibly can turn it into its opposite, to flip it over the origin. But it doesn't really change the overall direction. It doesn't change the line on which that vector resides. Those of you who are also taking linear algebra with me this summer will be able to say, for example, that this line is the span of the vector v. It's the set of all linear multiples, linear combinations of the vector v. And so when I multiply a vector by a scalar, it all stays in the same line, the same span of that original single vector. So that's what addition, subtraction, scalar multiplication can do. We can measure distances, we can measure lengths, and today we're going to get more geometric by talking about how to measure angles and how to measure areas. And to do that, we are going to introduce these 2 types of products that we can create with vectors. The first one being the dot product, the second one being the cross product. And when I talk about this, I talk about it in a little bit different way than the authors of our book do, because I have these sort of 2 different ideas of cross product that I want to talk a little bit about. One idea of a cross product that we can actually use in 2 dimensions that I call the scalar cross product. And then the vector cross product, which is what our textbook authors just call the cross product. It's the usual cross product that exists in 3 dimensions. So just to kind of set the table a little bit, the dot product is going to be our foothold into computing angles between vectors. So any question about angle, we're probably going to answer using a dot product in some fashion. Dot product is also, we'll see, going to give us a way to talk about length. So it's going to connect back to our discussions of magnitude, or norm, however you like to say it, that we talked about in our last class. And the cross product is going to give us the idea of area. So if I want to compute the area of something, the cross product is going to be a way to do it. One cool thing about the dot product is that we can use a dot product in the way that we define it today in any number of dimensions. So in any n-dimensional space, we can define a dot product and compute it in exactly the same way that we're computing with 2- and 3-dimensional vectors today. The cross product is different, though. We can define some kind of notion of a scalar cross product that I'll talk about in 2 dimensions, as well as a vector cross product in 3 dimensions. But beyond that, we are not going to know how to take a cross product of vectors in 4 dimensions, or 6 dimensions, or 10 dimensions. It's a bit more specialized. And there are a variety of reasons for that, some of which are quite superficial and some of which are actually quite deep mathematically. It turns out we can only define a reasonable notion of cross product in dimension 3 and in dimension 7, but not in any other dimension other than that. I guess dimension 1 if we're thinking about complex numbers. But yeah, that's it. Dimensions 1, 3, and 7 we have a cross product, but everywhere else we don't, which is mathematically a very deep result, and one that we're not going to get too lost in. For our purposes in multivariable calculus, the vector cross product is only going to be something we do in 3 space. So that's going to be where we spend the first sort of act of our class today. And in the second act, we're going to take all of our newfound information about vectors and how we can use vectors to do arithmetic and describe geometry, and use that to look at how do we determine equations for lines and equations for planes, particularly thinking about in three-dimensional space, because we probably learned a long time ago in college algebra or whatever how to describe equations of lines in 2 dimensions in the xy plane. And so today we want to bring that up into the 3rd dimension. How can I write down an equation that describes a line in 3 space? And also, how can I write down an equation that describes a plane in 3 space? We saw some examples yesterday of examples of equations of planes that were parallel to one of the coordinate planes. So x equals 2, for example, was an equation of a vertical plane in xyz space. So we've already seen some examples of equations for planes, but what if we want a plane that's not parallel to one of the coordinate planes? If we want it to be sort of tilted or oriented in some fashion, how do we write down an equation for a plane like that? So in a way, what we're kind of doing is we're trying to build up to calculus by first studying the sort of linear type objects, right? Just like in algebra, when we study lines first, and then we might be able to study parabolas and curves and things like that, we're doing the higher dimensional analog of that. We're figuring out how to talk about lines, which are kind of straight objects, and planes, which are kind of flat objects. So they're linear things, so that we will be able to use lines and use planes as approximations to curvier surfaces and curves inside of 3 dimensions when we get to the differential calculus portion of our course, which happens next week. So that's the foundation that we're laying. Vectors as a foundation for the study of lines and planes as a linear foundation for the study of nonlinear things, which we need derivatives to look at in calculus next week.